Alright, this video is over rational functions. So a rational function is just like a rational number. Remember, a rational number is a number that can be written as a fraction. So a rational function is a function that has a numerator and has a denominator. So we have a numerator that is a function, and we have a denominator that is a function. So both of them are functions. So we use n of x and d of x, n for numerator, d for denominator. Now when we have one of these rational functions, there are several topics, several things, there are several ideas that we need to analyze with that function. I'm going to go through them in this video. The first is the domain. The domain must exclude any values that make the denominator 0, even if they also make the numerator 0. Any of these values that make the domain not workable or not nice and perfect need to be excluded. Sometimes they are called excluded values, so the values that needed to be excluded. Alright, that's pretty easy. We've worked with domain before. So next up are zeros. Zeros, these are values that make the numerator 0, unless the number also makes the denominator 0 as well. And we'll show an example of that. Now, for example, if I'm looking at this function right here and I need to find the zeros, I'm trying to figure out what number makes the numerator 0. And 2x minus 3, and I could add 3 and divide by 2, so 3 halves becomes my 0. Now, what's my excluded value? My excluded value would be negative 4. Negative 4 makes the denominator 0. I must exclude that from my domain. So my domain would be all numbers from negative infinity to negative 4. Skip over negative 4 and continue on towards infinity. However, my 0 comes from the numerator, and that would be 3 halves. Okay, here's another function right here. This one would be a little bit easier to understand if I can go ahead and factor it. So I got x plus 4 times x minus 4. Always factor the numerator and denominator to make your life a lot easier. And what I realized here is that right away I have an excluded value. Negative 4 needs to be excluded. It makes the bottom 0. I cannot stop that. I cannot prevent that from being an issue. That's definitely going to affect my domain. And my domain would be negative infinity to negative 4, negative 4 to infinity. Okay, but notice that those two factors cancel, and I end up with just x minus 4. Now, that doesn't stop negative 4 from being excluded. It was still part of the original problem. I cannot be negative 4. However, this makes there only be one 0. The only 0 is at 4. So the 0 is at 4 because 4 makes only the numerator 0. Obviously, 4 minus 4 is 0. Negative 4 is an extra special value. We're going to talk a little bit more about that value later in the video, but it still needs to be excluded because it doesn't happen. It makes the denominator 0. It's not a very good number. But be careful, negative 4 originally looks like it would be a 0, but remember we need to exclude it. So the only time that this happens is when you have a number that makes the top and bottom 0. Those numbers are excluded, but they don't become zeros. Alright, let's look at one more example here. We have x plus 4. On the bottom I have x plus 4 times x minus 4. So very similar to the function above, but I flip-flop the denominator and numerator. So once again here, there are two numbers this time. I cannot be negative 4. I cannot be positive 4. Both of these numbers need to be excluded from my domain. So my domain would be negative infinity to negative 4, negative 4 to 4, and then 4 towards infinity. Okay, so both numbers must be excluded. Now, also, that x plus 4 factor cancels. So there is nothing left on top. So this, the only thing left on top I guess would be a 1. So this would work out to 1 over x minus 4. So this means there are no zeros because after I fully analyze the rational function, there is no number that will make only the top 0. So be careful. Zeros are numbers that make only the top 0, not both. If you make both the bottom and the top 0, you are an excluded value that's actually very special that we'll talk about here. Alright, so we have this idea of discontinuity. So a continuous graph is a graph that, like we talked about, polynomials, where the graph is continuous. You could draw the entire thing without lifting up your pen or pencil. So a discontinuity are spots where the graph is not continuous. There are two different types of discontinuities. The first type is a vertical asymptote. These are called essential discontinuities. So remember, an essential discontinuity is a vertical asymptote. Let me go ahead and show you with an example here. First, I'm going to go ahead and factor. It's always a smart idea to factor your numerator and your denominator. In fact, that's the first thing you should always do with any rational function. It makes the analysis of it a lot easier. Okay, so let's see here. I clearly get one number I know I cannot be. I cannot be 2. 2 needs to be excluded. This is what we call a vertical asymptote. I call it a VA for vertical asymptote. This is a spot on the graph that's a vertical line that I cannot cross. So when the graph hits it, the graph has to either go up towards infinity or the graph has to go down towards infinity. But it's a place where I have to lift up my pen. I have to lift up my pencil in order to draw it. That is a essential discontinuity. I do have two zeros here, 5 and -4. We'll talk about how to graph those a little bit later, but right now we're just talking about the discontinuities. The discontinuity is a vertical asymptote if it makes the denominator 0. Only the denominator 0, like 2 does in this case. The next type of discontinuity we have is called a hole in the graph. This is called a removable discontinuity. This is literally, here's the graph, and there's literally a hole in the graph. There is one spot, just one spot, where the graph does not exist. This occurs when you have a factor on top and bottom. So let me go and factor this for you. X minus 5 times x plus 4. Again, I've said it several times in this video already. Always factor x minus 4 times x plus 4 on the bottom. Okay, now let's analyze this real quick here. Two numbers I must exclude. I must exclude 4. I must exclude -4. Both of those make my denominator 0. But the x plus 4 gets canceled out, or gets removed. That's why it's called a removable discontinuity. So that makes 4 right here an essential discontinuity, which is a vertical asymptote. So I am going to have a vertical asymptote at 4 because it makes only the bottom 0. That's a type 1. Type 2 is it makes both the top and the bottom, the numerator and denominator, 0. That's -4. So -4 becomes what we call a removable discontinuity. Okay, removable discontinuity creates a hole in the graph. Now, this is the x-coordinate of that hole. So that hole's x-coordinate will be at -4. To figure out the y-coordinate of that hole, now this is a little bit tricky to understand because it's a hole. So there isn't really a y-coordinate. In fact, it's empty, right? I mean, look at this spot right here. It's literally an empty hole. But you need to know where that hole is at. So you're finding the point where the hole is at, even though there is no point there. Hopefully that makes sense to you. So once you identify that -4 is removable asymptote, or I'm sorry, the removable discontinuity because it made the top and the bottom 0, right? How do you find the y-coordinate is you plug that -4 into what didn't cancel. So -4 minus 5 is -9. -4 minus 4 is -8. So I get 9/8, positive 9/8. So the hole is actually at -4, 9/8. Now again, this does not exist. This is a point that's not really there, but you at least need to identify where that point that is missing is at, if that makes sense. So let's recap this real quick because it's a little bit confusing. And I want it to make sense. There's two types of discontinuities. The first type is an essential discontinuity. These are vertical asymptotes. These are numbers that make only the bottom 0. So they are essential to only the bottom. They only make the denominator 0. A removable discontinuity is a hole in your graph, and this comes when you have a value like -4 that makes the top and the bottom, the numerator and the bottom, become 0. So that gets canceled out, but because it gets canceled out or removed, it creates this hole in the graph. Hopefully that makes a lot of sense. All right, up next I want to talk about horizontal asymptotes. Horizontal asymptotes are horizontal lines that we cannot cross. Obviously horizontal lines go like this, but we traditionally make them dotted because there are lines that are not really there, but we know we cannot cross them. These are function values y that the function cannot be. So a lot of kids don't quite understand what horizontal asymptotes are. Just remember that they are values that you cannot be. These are y values that cannot be. Now, to analyze and determine if you have any horizontal asymptotes, you must compare the degrees of the numerator and denominator. So what you want to do is you want to look at the degree of the numerator versus the degree of the denominator. If the degree of the numerator is smaller than the denominator, y equals 0 is automatically your horizontal asymptote. Once again, here's an example. The degree of top is linear, has a degree of 1. The degree of the bottom is a quadratic, it has a degree of 2. So because the top degree is smaller than the bottom degree, you automatically have one at y equals 0. That means your x-axis, right, that is y equals 0, the x-axis, is your horizontal asymptote. Okay? Now, the reason for this is because that is a line you cannot be. So your function will never ever be 0. Your function will not allow it to be 0 when this happens. Okay? So hopefully that makes sense. When the degree of the numerator is smaller, Then the denominator, you have one of these horizontal asymptotes. Now, horizontal asymptotes are a little bit tricky. We'll explain a lot more in class, but that's the general idea. Now, what if the numerator and the denominator have degrees that are equal? If your degrees are equal, and here's an example right here, the degree of the top is a quadratic, that's a square. The degree of the denominator is also a quadratic, that's a square. They are the same. This is where you look at leading coefficients, okay? So your horizontal asymptote is the leading coefficient of the top divided by the leading coefficient of the bottom. So for our example here, the leading coefficient of the top is the 3. The leading coefficient of the bottom is the 2, so our horizontal asymptote is at 3/2 or 1.5. So at the straight line, the horizontal asymptote, the straight horizontal line is at 3/2. And again, that is what happens when your degrees are tied. You look at the leading coefficients. Okay? All right. The final example is if your numerator's degree is larger than the denominator's degree. Now, this is called an improper rational function. And improper is when your numerator's degree is larger. So kind of like an improper fraction, like 5/3 is improper because the numerator is larger than the denominator. So it's when the numerator's degree is larger than the denominator's, you have an improper fraction. Okay, or an improper function. This does not have a horizontal asymptote, so no horizontal asymptote. I call them HA, so no horizontal asymptotes. This creates a slant asymptote. This is actually a line that is slanted that you cannot cross. So it's not vertical, it's not horizontal, it's slanted. Some books call them oblique asymptotes. Oblique is just a fancy word for slant. So, to find the slant asymptote, you need long or synthetic division to actually find the equation of this asymptote, because this is a y equals mx plus b equation, right? You guys remember that? Y equals mx plus b, that's the equation of a straight line. So, when you have an improper function like this example I have right here, 2x squared minus 5x plus 6, all divided by x minus 3, this is going to have a slant asymptote because the top degree is 2 and the bottom degree is 1. The top degree is bigger. So to find your slant asymptote, I'm going to use synthetic division here, where I'm going to put the coefficients at the top, 2, negative 5, and 6, and I'm going to use the 0 from the bottom. Just like we use synthetic division, the 3 goes on the outside. That's the number that makes the denominator 0. Drop down the 2, 3 times 2 is 6, add those together, I get 1, 3 times 1 is 3, and I get 9. Now, this is the remainder, the 9's remainder, not needed whatsoever. Don't need it at all. What you need is the 2 and the 1. This tells me that my slant asymptote is at y equals 2x plus 1. Okay, so the actual line, so if I were to make my graph here, the actual line that is up 1, and then it has the slope of up 2, right 1, up 2, right 1. So this line right here is a slant or a vertical asymptote that I cannot cross. So when the graph comes to it, it must slide off it or slide. It cannot cross through that vertical asymptote, and we're going to see that in some examples. This, again, quick recap, happens when the numerator's degree is larger than the denominators, and to find the actual equation of that, you must use long or synthetic division to find the equation of that asymptote. All right, that's it. So let's look at some examples now. This is if you want to kind of practice things out. You could hit pause and then come back and check your work. So let's actually go ahead and analyze this function, 2x squared over x squared minus 1. First thing I'm going to do is completely factor the top, which is pretty easy, 2x squared. And the bottom, I'm going to do x plus 1 times x minus 1. Okay, first off, excluded numbers. X cannot be 1. X cannot be negative 1. So my domain is going to be all numbers starting at negative infinity to negative 1, and then from negative 1 to 1, and then from 1 to infinity. Okay, my zeros come from the numerator. What numbers make the numerator 0? X equals 0 or 0, 0. 0 makes the numerator 0 right there. Now, be careful. This is something that we've already learned. That is a multiplicity of 2s. This is going to be a touch 0. At 0, we're going to just touch. We're not going to cross, okay, because that's multiplicity of 2. So that's more information that we've already learned, which is cool. All right, what about our types of discontinuities? Because negative 1 and positive 1 only make the bottom 0, we have vertical asymptotes. These are essential discontinuities at x equals 1 and x equals negative 1. Those are vertical asymptotes. Again, these make the they make the denominator only 0. Nothing was canceled out, nothing got removed, so there's no removable discontinuities. These are essential, which are vertical asymptotes. All right, let's see about my horizontal asymptotes, HA, horizontal asymptotes. Well, the degree on top is 2, the degree on the bottom is 2, so I'm going to look at leading coefficients. The leading coefficient on the top is 2, the leading coefficient on the bottom is 1, so my horizontal asymptote is at 2. All right, the only other thing I want to be able to find is the y-intercept. A y-intercept is very easy to find. All you got to do is plug in 0. When I plug in 0, I get a 0 on top and a negative 1 on the bottom. So that means when I plug in 0, I get 0. Okay, and that makes sense. If you have a 0 at 0, 0, then you also have a y-intercept at 0, 0. It's the only point in the world that could be both a y-intercept and a 0 at the same time. All right, so here I go. I'm going to draw in my asymptotes first. Horizontal asymptotes is at 2. So I'm going to come here at 2 and make a dotted line that goes straight across to 2. And then I'm going to come over here to do my vertical asymptote. So I have one at negative 1. And I also have one at positive 1. And again, this is kind of tight in there, but you can see this. That's why I'm using these red lines here, making little dotted lines there. Okay. I'm also going to come now in, and I'm going to fill in my zeros. So I have a 0 at 0, 0. There it is right there. I know it's a touch 0, so I must do this. I must open down, kind of like a little tiny parabola inside there. How do I know I don't go up? Because then I would cross the asymptote. And I also know that I turn around there and touch because the fact that I have a multiplicity of 2. And lastly, what about the rest of the graph? Well, this part of the graph must be over here, where it's an asymptote, where it is getting closer and closer to the vertical and the horizontal asymptote, and same thing over here. A lot of kids ask, well, how do I know it's not down here? Well, think about this for a second. If the graph was down here, then it would have to cross the x-axis somewhere over here. Well, I don't cross the x-axis because the only place I cross the x-axis is my only 0 of 0. So obviously there's no way the graph is over there. So again, there should be some symmetry to this. I didn't realize how poorly I drew this picture, but these two graphs over here that I drew in blue should definitely be symmetric and nice over there. Okay, let's take a look at another one here. First thing you should always do to analyze these is go ahead and factor. So let me factor this guy. Let's see here. I get x and 2. I got x and 1. And let's see, I'm going to need a positive 2 and a negative 1. That way I get that positive 1 in the middle, negative 2 on the outside. And let's see, this is going to be x minus 3 and x plus 2. Okay, so I got a lot going on here. First off, let's start analyzing. I have two numbers that I cannot be. I cannot be 3, and I cannot be 2. Negative 2, sorry. I cannot be 3, and I cannot be negative 2. So my domain is going to be negative infinity to negative 2, and then negative 2 to 3, and then 3 to infinity. Okay, now the x plus 2 does cancel, so let's talk a lot about this. First, I have a vertical asymptote, an essential discontinuity at x equals 3. Okay, vertical asymptote at x equals 3. Now, at x equals negative 2, I have a hole, or I have a removable discontinuity. It got removed. Now, the hole is a specific point that I cannot be, but I want to be able to find that point. That point is at negative 2. How do I find where the y-coordinate is? Well, whatever didn't cancel, that's the x minus 1 and the x minus 3, whatever didn't cancel, plug negative 2 in. So if I plug negative 2 into that, I get negative 3 on top, and I get negative 5 on the bottom, which gives me 3/5. So at negative 2, 3/5 is where that hole is. Once again, it's a hole because it got removed. It's still a discontinuity. It still needs to be excluded from the domain, but it's just a different type of discontinuity. So we have a vertical asymptote, and we have a hole. Okay. How about zeros? Zeros are anything that makes only the numerator 0. So it looks like I have a 0 at 1. Again, why not negative 2? Negative 2 is our special hole, so please make sure you understand that. And let's talk about my y-intercept real quick. A y-intercept is what happens when you plug in 0. It's actually easier to do this into your original function. So if I plug in a 0, I get a negative 2 on top and a negative 6 on the bottom, which reduces to 1/3. So I have a y-intercept at 1/3 there. So let's go ahead and graph everything here so we can make sense of all this. All right, so at x equals 3, I have a vertical asymptote. Okay. and I have a hole at -2 3/5. So at -2 3/5, and again, somewhere right around there. It's kind of hard to show exactly what it is, but I do have a hole. I did actually forgot to find the horizontal asymptote. I apologize. Horizontal asymptote, my degree on top is 2, degree of the bottom is 2. So because they're tied, I'm going to look at leading coefficients, which is 1/1. So my horizontal asymptote is at 1. And let me go ahead and draw that in there. So there's that asymptote right there. Okay, the only other thing I got to go ahead and put on my graph is the, let's see here, the 0 of 1. So here it is right here. So here's the graph, right? It's going to come in hugging this horizontal asymptote. It's going to go near the hole and just kind of go through it, but not actually go through the hole, if that makes sense. Going to cross that 0 and come down. And notice that I did have that y-intercept at 1/3 in there as well. And then the other part of the graph must be up over here somewhere. Why can it not be down here? Because then it would be forced to cross the x-axis, and I know that I don't cross the x-axis anywhere over there. Same thing, it cannot be up here, because if it's up here, I'm going to violate the fact that it's a function. And remember, if I have a graph up here, then I'm not going to pass the vertical line test. Also, it would show that I have another y-intercept, and I can only have one y-intercept. So hopefully that all makes sense there. So this is a good example that has everything. Horizontal asymptote, vertical asymptote. It's got a hole. It's got two different types of discontinuities. But remember, -2 and 3 both need to be excluded from the domain because they're both excluded values. They're values I cannot be. All right, let's do, I think this is our last example here. All right, so one time I'm going to go ahead and factor first. That's obviously always the first and most important thing. So I get this function right here. Nothing cancels, which is very nice, but I do have an excluded value. I cannot be -1, so -infinity to -1, and then -1 to infinity. Okay, so that is a vertical asymptote at x equals -1 because it did not cancel. It is on the bottom, and it is a value I cannot be. Let's see here. Let's talk about zeros. There are two numbers that make the top 0, 0 and... Sorry about this announcement here. I'll keep going. 0 and +1 are my two zeros. And they both have multiplicity of 1s. They're both cross zeros. So they're both going to cross at those points. And let's see here. Y-intercept can be found by plugging in 0 for x. When I plug in 0 for x, I get a 0 on top and a 1 on the bottom, which is 0. And that makes sense because I have a 0 at 0, so I would have a y-intercept there as well. And lastly, what about horizontal asymptotes? Well, there are no horizontal asymptotes because the top degree is bigger than the bottom. So when the top degree is bigger than the bottom, this is our special case where we have a slant asymptote. So to find that slant asymptote, I'm going to use synthetic division here. I'm going to put a -1 on the outside. That's the 0 from the denominator. Use my coefficients of 1, -1, and 0. Don't forget I have to have a 0 for that last spot there, that filler spot. Drop down the 1, multiply, I get -1, add, I get -2, multiply, I get 2, or multiply, I get 2, add those, you get 2. This is your remainder. You don't need the remainder at all. And I have my oblique, or my slant asymptote at y equals 1x minus 2. Y equals 1x minus 2. So I'm going to go ahead and draw that vertical asymptote at -1. That's pretty easy to draw in there. I wish I could draw a little bit straighter. I apologize. Okay, let me draw that horizontal asymptote. So horizontal asymptotes, again, it's a slant line I cannot cross. So it starts at -2. That's the y-intercept. The slope is 1/1. So that's up 1, right 1, up 1, right 1. So it's going to go like this. It's also down 1, left 1, down 1, left 1. So it's going to go like this. You don't have to get extremely accurate with drawing that, but it should be pretty accurate based on the slope and the y-intercept. Okay, now let me go ahead and fill in here my zeros. Here's 0, 0, and here's 1, 0 and 1. And let me go and fill in my y-intercept, which is also 0, 0, so that was easy. And this makes sense now. So here's the graph. It's going to hug that asymptote. It's going to come down here. It's going to cross through 0, cross through the 1, and then continue back up and hug. And again, my line is really wavy, but it should be nice and curved there. Now, where's the rest of the graph? Well, it's got to be stuck over in here, Because if the graph was anywhere else, then I would cross the x-axis. So imagine if the graph was, I'm just going to draw it in here. Imagine if the graph was over here, then it would cross the x-axis, which I don't do anywhere over here. Same thing, imagine if the graph was over here, then I would cross the x-axis, which I don't do. So that makes the graph in these two spots with these, when you have these slant asymptotes, the graph is always going to be across from each other. So if the graph was in this top right area, that's going to be in this bottom left area. They're always across from each other. They're never side by side. So hopefully that was a nice video there that kind of explained a couple different ideas that come up with these rational functions. Please make sure you take good notes, and we'll look at several examples in class, but you need to be able to identify vertical asymptotes, horizontal asymptotes, slant asymptotes, zeros, domain. And you got to be able to address the fact if you are an essential, removable, discontinuity. So essential is a vertical asymptote, but removable is where we have these holes. So make sure you understand the difference there as well.